Hello everyone, welcome to lecture 2 of mathematical modeling and simulation. So let's begin. So this lecture is all about understanding the process of mathematical modeling, and specifically we will be focusing on dimensional analysis. So before starting, let's have a quick recap of what we have already covered in lecture 1. So in lecture 1, I covered that what is mathematical modeling and why do we do mathematical modeling. In fact, we put forward 3 questions there in lecture 1: what, why and how, and what part and the why part we have already answered in lecture 1. So from this lecture onwards, we'll be exploring the third part, how to do mathematical modeling. So I'll be giving you few techniques on performance of mathematical modeling, specifically focusing on one of the techniques, which is dimensional analysis, followed by few applications of it, and then we will be defining principle of dimensional homogeneity, which is a fundamental principle governing whole process of dimensional analysis. And then I'll introduce some basics of it, followed by some illustrative example. So first question we need to answer is how to do mathematical modeling. So there are basically 4 methods of performing mathematical modeling, and before actually telling you these 4 methods, I will declare here that these are not the only techniques or the only ways in which a mathematical model can be constructed or formulated. It really depends upon the context of the underlying real world phenomena for which you are making a mathematical model for, that there can be entirely a different technique can be used for that particular problem. Like these 4 techniques can be used independently also, or they can be used in combinations also, but it's not mandatory that all of them have to be applied for one particular problem. So let me give you these 4 techniques. The first one is dimensional analysis, which we are going to cover up in this lecture. The second is scaling. In fact, these two are related with each other, dimensional analysis and scaling. The third is conservation laws, and the last one is constructing linear models. So in this lecture, we'll be starting on dimensional analysis. In fact, the topic is big enough that I have splitted the content in 2 lectures. So this lecture as well as the next lecture, we will be focusing on dimensional analysis. So let's explore what is dimensional analysis. So similar to the concept of mathematical modeling, here also we'll try to figure out the answers to these 3 questions: what it is, why do we do it, and how to do it. And exactly similar to the concept of mathematical modeling, the what part and the why part will be answered quickly, while how is going to take longer time. So let's first answer what is dimensional analysis. So let me begin with a formal definition given by a famous mathematician, H.L. Langar. It is a method by which we deduce information about a phenomena from the single premise that the phenomena can be described by a dimensionally correct equation among certain variables. So that means firstly we need to understand what we are actually trying to do. Before doing dimensional analysis, we have already figured out what real world phenomena we are going to study, for which process we are going to construct a mathematical model. So that is the phenomena here. And then we'll be trying to make an idea in our mind that what kind of equation or what kind of expressions will be there which will be explaining the phenomena very accurately, and those expressions should be dimensionally correct, and obviously these expressions are nothing but the relationships among the variables. So important word here is nothing but dimensionally correct. So as we proceed with the concept of dimensional analysis, you will be more and more clear about the complete idea of the dimensional analysis. By just reading this definition, it's difficult to understand or grasp the whole concept, but this was just a formal definition to make you aware of that the focus is on dimensionally correct equation, because in every phenomena there are always the physical quantities involved, like there can be temperature involved, pressure involved, or forces involved in mechanical models. So whatever underlying physical quantities are, they definitely have some units and dimensions, and whenever dimensions come into picture, so we have to make the equations dimensionally correct. So that's the whole idea of dimensional analysis, and it is based upon a fundamental principle which is known as principle of dimensional homogeneity, also known as principle of dimensional consistency, but in short we'll be calling it PDH. So let's have the definition of this principle. It says an equation. So obviously now we have, say, already an equation in front of us. An equation depicting the relationship between variables and parameters. So soon I'll be coming to this, that what is the meaning of this variables and parameters. In a mathematical model, that equation is said to be dimensionally homogeneous, dimensionally consistent. So whatever you can call it, dimensionally homogeneous, dimensionally consistent, or you can also call it dimensionally correct, if each term is of same dimension. So what essentially it means, that it does not make any sense to add apples with oranges. Actually, this is just a famous saying which is usually adopted. The analogy is adopted to make you understand the concept of dimensionally correct equations, that oranges cannot be added to apples because both of them are representing different physical quantities. More specifically, you want to understand it through mathematical example, then we can have example like, it does not make any sense to add time and velocity. You can create plenty of examples like that, but just to give you an example right now. So this is something already known to us because we have studied this principle of dimensional homogeneity in our earlier science classes in school days, that we need to add or subtract only those quantities which have the same dimensions. That's the clear meaning of this. And this principle is actually governing the process of dimensional analysis. So now we have answered what it is. So now we'll try to figure out, why do we do dimensional analysis? So there are many reasons to perform dimensional analysis. So we can also frame them in the language of that these are the objectives of performing dimensional analysis. That why do we do dimensional analysis is because of these reasons. For sometimes in certain examples, we want to derive relationship between variables in a model. Suppose in a particular model, you have already defined your variables. Like suppose you want to model the motion of a freely falling object. So you want to see what expression is going to be representing its motion. So you will define your variables. Your variables will be position, velocity, and the time. So you want to know what is the relationship between these position, velocities, and time. So if you do not know those relationships, so in some cases the dimensional analysis will actually help you to derive those relationships. And then the another objective is to validate a newly formulated mathematical model. So the first case, you do not have the relationship, you will be entirely driving it using dimensional analysis. In second case, suppose you have already derived it. Suppose you are working on a new process for a certain process whose mathematical model does not exist, or you have tried to think of adding entirely a new term in the mathematical model, but you are not sure whether this is going to work or not. So the very first thing you have to do is to perform dimensional analysis over your mathematically formulated model to actually see that whether that equation is dimensionally correct or not. Because if that is dimensionally incorrect, then nothing else is going to work. So that's another application of dimensional analysis. And sometimes we do use dimensional analysis to identify relevant parameters in the model. So we'll be talking about this in more detail when we're doing the particular examples, that what do you mean by relevant parameters of the model? Because sometimes it seems to us that okay, this particular phenomena is depending upon temperature also, it depends upon pressure also, it's depending upon humidity also. So there can be many factors involved, but usually the conclusion turns out to be that only one factor is a controlling parameter, rest all are superfluous, they are not necessary. So dimensional analysis helps us to make decisions about that which particular parameter to be included in the model and which is not required at all. So for this also we'll be doing examples. And then we have this objective or this reason of performing dimensional analysis. It also helps us to reduce the number of variables and parameters. In fact, this is related with this, but it is more specifically related with the process of scaling, which I told you that dimensional analysis and scaling are connected with each other. So this also will be checking up. So this is about why do we do dimensional analysis, because there are many benefits of performing dimensional analysis. They entirely change the complicated looking like structure which is in our mind and helps us to simplify the model to much better extent. And after performing dimensional analysis, we usually starts with the further analysis or solving the model or whatever follows after that. And then we talk about the applications of dimensional analysis. So there are many applications, because most of the times these models are used in those areas where we have forces involved, Newtonian mechanics involved. So most of the time they have application in all those fluid mechanics, mechanical engineering type of subjects. They have the major applications in those kind of areas. It's clear from these also. So the major applications are in aerodynamics, ship designing, heat and mass transfer, fluid structure interactions, astrophysics, nuclear blast, and surprisingly biology and economics. So there are much more dimensions of the word dimensional analysis, and it has many applications. That's why its understanding is very fundamental and essential if you want to learn the command of mathematical modeling. So now we have already answered that what it is and why do we do this. So why had many reasons, because it has many benefits or it has many applications. So you want to be an expert in a particular area, so the first thing you need to know is mathematically modeling it, and in the mathematical modeling process you need to know how to perform dimensional analysis. So now we need to learn this, that okay, now I have decided I will perform dimensional analysis, but how to perform dimensional analysis. So now we are coming to this question. So the how part will start from some basics of dimensional analysis. So the first thing, if you look at the definition which I just gave you, that involved the term variables. So first I need to explain you what is the meaning of the word variable and what is a parameter. Most of the time everybody is confused about, okay, what is a variable and what is a parameter, what is the difference between them. So the definition or the concept which I am going to define here, it may differ from subject to subject. For example, in the language of programming languages, the variables and parameters have different meanings. In the language of statistical mechanics or in the language of probability and stats, there the variables and parameters have entirely a different way of defining. They have entirely different meaning. So, but I am going to give you here the concept of variables and parameters in the context of mathematical models. So do not get confused if you see a conflicting definition. Actually that will not be conflicting, but it can be a little bit different from what I'm going to give you here. So it's firstly, okay, let's first talk about what is a variable. So it's otherwise clear from the name. A variable is something that varies. You know, before defining variables and parameters, we should know what is a constant. So obviously nobody needs to tell you what is a constant. 3 is a constant, 4 is a constant, e is a constant, pi is a constant. So we know these are the constant values. The numbers which we can see in front of our eyes, they are just the constants. And after constants, we have variables and parameters into picture. So variable is something which varies. It changes its value. So variable is you can say it's an entity or it's a quantity which changes its value. While if you talk about a parameter, so parameter is basically defining a class of equations. So let me be very specific with it. So let me give you an example to understand the clear-cut distinction between variable and parameter. So if I'll give you this equation, y is equal to mx plus c, then can you figure out that which one is constant, which one is a variable, and which one is parameter? Right now in this equation, I do not see any constant. The m and c, both of these are my parameters. Because on varying m and c, I'll get a class of equations. And obviously, I need not tell you what class of equations it is representing. It is representing the straight lines with slope m and y-intercept c. So my m and c are the parameters. If I give a different value of m and c, I'll get a different straight line. I'll change the value of m and c, I'll get a different straight line. So they are my controlling parameters, but otherwise they are acting like constants. But in general, they represent a class of equation. To give you one value of a straight line, one equation of a straight line, you will fix the value of parameters. So here these are the parameters, but they have taken constant values. That's why most of the times we get confused between, okay, sometimes it's a constant, sometimes it's a variable, but parameter is something in between the variable and constant. They do have the flexibility of varying them, but while defining one particular mathematical expression, they have fixed values. So in general, they define a class of equations, but for one particular equation of that family, their values are fixed. So they are called the parameters. And if you talk about what are the variables here, so my y and x, these are the variables. So variables are something which are varying with time. I am changing x, x is changing, and obviously corresponding to x, y is also changing. So variables are changing their values. So let me be now summarizing it in another way. So we are now clear with the meaning of the word variables. So variables can be further classified as independent variables and dependent variables. So it's very obvious, we are already familiar with this, but it's very convenient to identify what variables are independent and what are dependent. It's very essential step of dimensional analysis. You should know that what is controlling what. For example, you are studying a weather forecasting model, so we know the temperature is varying with respect to the space as well as time. The temperature at day is different from temperature at night, so it varies with time. And the temperature in Delhi is different from temperature in Patiala, so it varies with respect to space. So the space and time are my independent variables, while the temperature is my dependent variable. So whenever you are going to study some mathematical relationships, so you should know which one is the dependent and which one is the independent variable. And similarly, if you talk about parameters, so they also can be divided in two categories: adjustable and non-adjustable. So adjustable is something which you can adjust. So adjustable is also known as the controlling parameter. So this is something, the time is the controlling parameter here, or you can say you're computing the energy. So energy is depending upon the initial velocity, because if you're say talking about kinetic energy, so kinetic energy is given by this expression. So the velocity is the controlling parameter for the kinetic energy. So whatever sense you can understand. So controlling parameter is something which is in control of us. We can control how it's going to have effect on something dependent on it. And non-adjustable parameters are those parameters which we cannot change. For example, g, the value of acceleration due to gravity. This is something I cannot control. So although there will be the model parameters will be depending upon the acceleration due to gravity, it should have the direct involvement in my expressions, but this is something I cannot control. So this is a parameter which is having a constant value and it's a non-adjustable parameter. So that's the brief idea about understanding of variables and parameters. So after this understanding, now we need to define the fundamental quantities. So fundamental quantities, these terms are I hope already clear to you because you have studied this in your school days. So we know that we have these fundamental quantities with us: mass, length, time, and we have temperature and current. In fact, there are more, but here I'm just giving you these 5 quantities because most of the times we are just done with using these quantities. So the dimension of them is denoted by m. Mass, we know the dimension is denoted by m. Length dimension is denoted by L. Time is denoted by T. Temperature, we have entirely a different symbol. And for current, we have I into picture. And obviously in most of the example, we'll be using these 3 fundamental quantities. So fundamental quantities are those quantities, like all the other quantities, all the other physical quantities can be obtained by using the combinations of the fundamental quantities. So those quantities are known as derived quantities, which can be obtained using the product of the fundamental quantities. So you can have many derived quantities, for example area, volume, and then you can have velocity, acceleration. So there are plenty more. You can create many derived quantities. The area dimension is going to be L square, volume is definitely L cube, velocity is, we know, Lt minus 1, and acceleration is Lt minus 2. So there are, the list is infinite, so you can create many derived quantities yourself. This is just revising you the fundamental terms. And then we have the third kind of quantities, which are dimensionless. So dimensionless quantities are which have no dimensions. For example, number, like say I write 3. So it just makes sense, it's 3. It does not have any dimension. Say if I write another quantity, angle. How do you measure angle? Angle is something measured in radians. It does not have any dimension of its own. Similarly, there are constants like pi, e, the universal constants which have fixed values. They also do not have dimensions. And we'll be also looking at many other quantities which will not be having dimensions. So that will be coming in specific examples, that there are actually plenty of dimensionless quantities. In fact, they further can be categorized into 2 categories: dimensionless quantities with units and without units. Anyways, right now we just need to focus on what it is. So these are some important points about the derived quantities which you can read. Sums of derived quantities with the same dimension are derived quantities of the same dimension. So it simply means, we know that area plus area is going to be area. So the dimension of area is L square. So obviously on this side also the dimension is going to be L square. Products and ratio of derived quantities are also derived quantities. We know that this velocity is a derived quantity, which dimension is Lt minus 1, and acceleration is also a derived quantity. So if you multiply or you divide by them, so they are also turns out to be the derived quantity representing some other quantity. Then we have this, which is important. We need to understand it here, that a derived quantity is dimensionless if its numerical value remains invariant when the base units are changed. So because I just told you, if you multiply or divide the derived quantities, you may get entirely a new physical quantity which may or may not be having any dimension. For example, suppose there are 2 kinds of velocities involved in your model. Say one of them is the particle velocity. So there are 2 kinds of particles. One velocity is of particle 1, another velocity is of particle 2. This is a hypothetical example I have just created to make you understand. So we know that velocity on divided by velocity will be equal to something dimensionless. So what physically it will be representing, that can be a constant, because when you divide the same dimension quantities, definitely you are going to get the dimensionless quantities. Or another way to obtain dimensionless quantity is this, like Vt by L is also dimensionless. V is velocity, its dimension is Lt minus 1. Time, the dimension of time is T divided by L. The dimension of L is, length is L. So if you do the calculation, so the dimension turns out to be 1. So the dimensionless quantities are always represented with their dimension 1. They are dimensionless. So that's the meaning of the dimensionless quantity. And then this is also need to be understood. Logarithmic, exponential and trigonometric functions, if you apply on the derived quantities, they are in general not derived quantities. For example, e raised to power area. So I do not know the physical meaning of this. So these kind of expressions, usually it's better to represent them into the dimensionless form. So we'll talk about this when we will encounter these kind of equations or expressions in our models. But right now you just need to understand this is what is happening. That if you differentiate or you integrate, then the derived quantity is preserved, but if you apply these kind of functions, log, exponential and trigonometric, then that sense of physical quantity is usually lost. We do not have, because these are just the mathematical operations, these are not taking us to another physical world. So let's skip this for the time being. We'll talk about in detail if we encounter any kind of this example. So moving ahead, I want to give you some examples of now dimensionally correct equations, and for that we need to relook at the principle of dimensional homogeneity, so which we just stated. So what consequence we can draw from principle of dimensional homogeneity? So it's very important. A dimensionally homogeneous equation is independent of the units of quantities. For example, you have formulated an equation, so it really should not depend upon what set of units you have chosen. Only then the equation is going to be dimensionally homogeneous. If on changing the system of units, your equation gets changed into an entirely new equation, so that means your equation is dimensionally not consistent. So that's a check, that's a way to know that whether our equation is dimensionally correct or not, and this is a consequence of the principle of dimensional homogeneity. So let's do this for an example to check whether a particular equation is correct or not. So let's have an example of free falling object which you have, say, just dropped from a certain height, and I know this equation is basically controlling the motion of it, where S is representing its position or the distance covered at particular time t, T represents the time, and G is obviously due to the acceleration due to gravity. So if you can figure out here what is a parameter here, what is a variable here. So T and S are the variables. T is time, is here my independent variable, while the position is my dependent variable because it is depending upon time, and the acceleration due to gravity is nothing but a parameter. Actually it's a fixed parameter, it's a non-adjustable parameter. So that's the equation. Now I want to see whether this equation is dimensionally correct or not, and for that we can see that the dimension of left hand side, this is position, distance, it's L. The dimension of right hand side, the acceleration due to gravity is having this dimension, and t square, the dimension of this. So the square bracket we represent the dimension is nothing but t square. So if you multiply gt square, this is going to be lt minus 2 t square. That's how the dimensions gets multiplied. It is giving out to be L. which is same as the dimension of the left hand side. So since dimension of left and right hand side is same, so therefore this equation is dimensionally correct. So this equation now I can call is an example of dimensionally correct equation. So now let's do certain changes in this equation. Now I know the value of g. The value of g is 9.8. So dividing 9.8 with 2 t square, this gives me this. So now my equation is modified to this. And if I want to know whether this is dimensionally consistent or not, so at first glance I see, okay, the left hand side dimension is L, but the right hand side dimension is t square. So I think that this is not dimensionally correct. This is dimensionally non-homogeneous. Why that information is coming to me? Because this 4.9 I am looking it as a constant, but not as a constant with units. This is just not a dimensionless constant, while this is a constant with dimensions, because we know that it is actually representing our g by 2, where g is nothing but having the dimension of acceleration. So this can be really misleading, that if you look at directly equations like this, then you may look or you may drop the conclusion that okay, this is dimensionally incorrect, but actually that is correct, because you have the constant in the picture is the constant with dimension. So what is the solution? So solution is to correctly represent it. So instead of writing it like this, you should always write your equations like this, because most of the times this question is asked that if we already know the value of certain constant, why we just don't plug in the value of the constant directly? Why we keep it as a parameter? This is the reason we keep it as a parameter, because it does not mislead to us that this is going to happen. So now c is the parameter which is g by 2. So I know the dimension of c is of that acceleration. So this is the correct representation of dimensionally homogeneous or dimensionally consistent equation. And now we talk about that fact which I just told you, that the dimensionally correct equation should be independent of the system of units. So this 9.8 was making sense only for those equations because it was 9.8 meter per second square. So that means your system of units is that length to be measured in meters, time to be measured in seconds. But if I change length unit from meter to say foot, then I know that 1 meter is 3.28 feet. So what's going to happen? So S is going to be 4.9 into 3.28 t square. So which is going to be 16.1 t square. So that means this is another way of understanding that why this equation was not dimensionally correct, because it was dependent upon the system of units chosen. On changing the system of units, my equation entirely changed into a new equation. So that is why the correct way of representation is this, when you have to represent it through dimensional constants, not with the simply constants. So that's what I wanted to convey, that what is the correct way of representing a dimensionally correct equation. So this is what I have summarized here. You replace all the numerical coefficients in the equation with the unknown dimensional constants. For example, which I have just explained you, suppose this was a picture. So whatever this is, instead of writing your equation like this, you write it like this. Now you want to know what is the dimension of this C. So you apply the principle of dimensional homogeneity and you will get to know the value of this, because you know S is L, T square is T square. So C should be LT minus 2. So it's very easy to calculate. In fact, this is a basic method of dimensional analysis to compute the dimension of unknown constants which are involved there. Okay, so we are left with one more example. Yeah, sorry, let me take one more example. So suppose it is found that the pressure distribution in Earth's atmosphere over United States can be represented by this formula. Say they have given you this formula. into e raised to power. So the correct way of representing it will be a, because this is something just a constant, this is a unit of it. So this is the correct way of understanding, where a is this and b is, plus per meter. And because z here is given to me, z is altitude. So altitude means height, it is measured in meters. So this b has to have the dimension of per meter, because only then b into z will be dimensionless, because this side it is pressure. So pressure is Newton per meter square. So the dimension of a is also Newton per meter square, as I can see that. So that means this figure should be dimensionless. So to make this dimensionless, so I have to match the dimension of, I have to adjust the dimension of b according to the dimension of z. It has to be just a number. So since z is in meter, so b has to be per meter. So that's why these are the two constants I defined, and this is the correct way of representing this situation. Okay, so that's all about this lecture. In next lecture, we'll continue with the dimensional analysis.